morning. The next session is the Joule-Thomson expansion. So we have already told when we are deriving the equation or when we are dealing with enthalpy that the enthalpy is a constant during Joule-Thomson expansion. This Joule-Thomson expansion is otherwise called a throttling process. Joule-Thomson expansion, or it is also known as porous plug experiment. That is, we have already discussed in detail about the porous plug experiment or the Joule-Thomson expansion. That is, we are maintaining the gas at a high pressure and temperature region. Then through some pores, there is a wall, porous wall there. Then we are moving by compressing the one side of the container, and at the same time we are expanding the other side of the container. Then this gas at the pressure Pi can be moved to another container having a pressure of Pf. That this Pf is always less than Pi. That throttling process we have discussed earlier. So I have told at that time that we can liquefy gases, especially nitrogen, etc., by continuous throttling process. So we can obtain this liquefaction or liquid form of the gases by the continuous Joule-Thomson expansion or throttling process. So the next session is the Joule-Thomson expansion. Or throttling process is also known as porous plug experiment. So for continuous Joule-Thomson expansion, we can use a pump actually. That means here this is a pump. So one side of the pump is a low pressure region. So that is a pump. This is a high pressure side and this is a high pressure side. And here we have this porous plug, etc. This is high pressure side. This is low pressure side. So what we are doing here is we are maintaining at first the high pressure side, the pressure is some Pi and the temperature is some Ti. So the low pressure side we are keeping the temperature as some P1 T1. Pf, that means some P1 T1. Some P1 T1. Then from high pressure side to low pressure side means you will get a temperature and a low pressure gas. So again what we are doing is the high pressure side we are maintaining at Pi Ti. So we can do the process for different values of low pressure side different low pressure P1, P2, P3, etc. So any gas we can cool like this. That means high pressure side means P initial, T initial side. This side is P initial and Ti side. Then this is some low pressure side. That means the low pressure is Pf and the temperature is Tf. So the pressure Pi, from the pressure Pi, Ti, we are moving to some Pf, Tf. That Tf may be P1, T1, and in the next case we are maintaining the pressure at P2, then the temperature will be T2, like that. So you will get large number of points for the same Pi, Ti. You will get large number of points and we can draw these points on a PT diagram. The pressure we are setting and the temperature is changing according to the initial pressure and the final pressure. So depending upon the initial pressure, that P1, the temperature will vary. And depending upon Pi, Ti and this T2, the temperature T2 may vary. So we will get a large number of points depending upon these quantities for our experiment. So we can draw a PT diagram and we can mark each points for Pi, Ti and P1, T1. We can mark 1 point. For initial Pi, Ti and final P2, T2, we can mark another point, something like that. The process is starting from Pi, Ti and ending at P2, T2, we will get another point. So we can draw that a PT diagram here. That is, this is the pressure and this is the temperature. And we are starting the experiment Pi, Ti. So the usual variation is like that. You will get large number of discrete points. This is P1, T1. So this may be some P2, T2. This may be some third point, and this is some fourth point. Then this temperature will decrease. Temperature will decrease. This is the fifth, and this is the sixth, and this is the seventh point. So you will get a large number of points like this. This is for a particular Pi. And finally, this 7 point means at this point the gas is very cool one. So a large number of points you will get by repeating the experiment. And each experiment we are maintaining the Pi, Ti a constant value. Then for the first case P1, T1, then maintaining Pi, Ti, then the pressure will be T2, then the temperature you will get as T2. So temperature is a dependent variable that depending upon these three Pi, Ti and P2, this T2 will depend. P2 is an independent variable that we are maintaining, we are setting the pressure. So the usual process is like that. At a particular, at first it may increase to a certain temperature, then it will decrease. So this is actually you can draw a locus. So this is not a curve, this is only discrete points. So what is the peculiarity of each point? The enthalpy is a constant for each point. That means Pi, Ti, what is the enthalpy at Pi, Ti? For P1, T1 also the same enthalpy. So enthalpy is a constant during a throttling process. So we have the pressure at certain temperature or at certain pressure, the temperature can increase, and from that point the temperature will decrease. This is the usual characteristic of a throttling process. So we can draw a locus. This is not the curve of. We can draw a locus. That means what is the peculiarity of this locus? The enthalpy is a constant. And this is not a curve of a throttling process. This is only the locus of all the discrete points where the enthalpy is a constant. So this curve, the locus of all the points in a PT diagram for a throttling process is known as, since the enthalpy is a constant, it is known as isenthalpic curve. Isenthalpic curve. This is not a curve of a throttling process, but only the locus of all the points. I am connecting the locus of all the points during throttling processes, and this curve is known as this. In this curve, the enthalpy is a constant. So all the points, the enthalpy is a constant. So this is known as isenthalpic curve. So we can calculate the slope of this isenthalpic curve. If you are taking the slope here, I am taking the slope here, that is the pressure, here the pressure increasing but the temperature decreasing. So you will get, for a constant enthalpy, the slope is dou T by dou P at H. And this slope is represented by the quantity mu, that is dou T by dou P P at H. This is molar enthalpy. For 1 mole I am talking. For molar, otherwise we have to write the capital H. So mu, this is dot T by dot P at H. This is known as Joule-Thomson coefficient. So for the same Joule-Thomson coefficient, and for the point 4, this is the maximum point, then this mu will goes to 0. That means maximum there will not be any change. So this mu is 0 at this 4th point. This is the maximum point here. Maximum point here. Then this Joule-Thomson coefficient will goes to 0. For this side, actually the increase in pressure or the decrease in pressure means there is an increase in temperature. So this is having a negative Joule-Thomson coefficient. For this side, pressure is decreasing, also temperature is decreasing. Here we can take this slope here. So the pressure is decreasing means the temperature is also this and this also decreasing. So mu is a positive value here. So this is mu is represented by dot T by dot P at a constant enthalpy for this isenthalpic curve. The slope can be, the slope is known as Joule-Thomson coefficient. So we can draw a large number of such curve for any gas. If we are changing the PITA, initial pressure value, to some other value, then the P1 T1 may not be the same P1 T1. So depending upon the initial pressure and temperature, the next pressure, if we are fixing the next pressure P1, then the T1 may vary. So like the initial pressure is some PI1, then the temperature is some TI1. Then the pressure, the second side PF1 and the temperature is some TF1. So if you are changing the initial pressure as PI2 to PI2 and TI2, then the pressure, final pressure, if we are maintaining at PF1, then the TF may be different. TF2 may be different. Or we can change the PF2 also. Then depending upon the initial values and this value, the temperature will vary. That is, the temperature is dependent variable and pressure is an independent variable. So we can draw different isenthalpic curve for the same gas. So we can draw a large number of curves, isenthalpic curves, starting with some PI, so different values of this initial condition. So for that we are usually drawing, keeping PI a constant for all the process, and T, the temperature, the initial temperature, a different value. So we will get different points. So this will be the first, you can draw, this is the first isenthalpic curve. This pressure is, we are keeping at PI, but temperature is a different value, PI1 we can write. So the next value may be this one. That is, the pressure is the same but temperature PI, the TI is a different value. This is the initial one and this is the final one. So this the next you will get the value, the curve like this, and the next you will get the curve like this. Same initial conditions, like that. So there are different maximas here. Here is the maxima, here is the maxima, here is the maxima, like that. So this is the usual change if we are dealing with different initial temperatures keeping the same initial pressure. So we can connect all these points. So in one side the Joule-Thomson coefficient is a negative value, this side the Joule-Thomson coefficient is a positive value. So we can connect the locus, connect the maximum, all the maxima here. All the maxima here. So you will get two regions. One is the region inside this curve and the other is the region outside this curve. And this curve is known as inversion curve. Inversion curve. Inversion curve is the curve which is connecting the maximas of all the isenthalpic curve. So this maxima for this isenthalpic curve is this one, maxima for this isenthalpic curve is this one, like that. So we are connecting all the maximas of the different isenthalpic curve. We are connecting using a curve, and this curve is known as inversion curve. The slope is positive. This region is known as region of cooling. This is the cooling region. And the region outside, here the slope is negative, or the Joule-Thomson coefficient is a negative value. So the region here, this region is known as region of heat. This is the region of cooling, and outside this is the region of heat. So we have the Joule-Thomson coefficient, which will be 0 at the maxima points, which is a positive at the positive values on the cooling region and negative value in the heating region. So we have three different values for mu in the same isenthalpic curve. This is the positive slope, negative slope, 0 slope. So next we can derive the equation for this Joule-Thomson coefficient, and what is the peculiarity of Joule-Thomson coefficient for an ideal gas and for a van der Waals gas, that we can derive.